Welcome to this explainer. When you look at an industrial chemical facility from the outside, it can absolutely seem like this chaotic, intimidating maze of steel and steam. But today, we're going to demystify all of that overwhelming complexity. We're going to break that giant maze down into a highly organized, easily understandable, step-by-step flow.
So here's our roadmap for today. We'll be exploring 1. The chemical plant ecosystem, 2. Phase 1, mixing and process reactors, 3. Phase 2, heating and cooling systems, 4. Phase 3, separation and refinement, and finally, Phase 4, flaring and safety systems. Let's start with a bird's-eye view of the ecosystem, and then we'll literally track the chronological life of a raw material as it transforms into a finished product.
All right, Section 1, the chemical plant ecosystem.
We have to begin our journey by looking at the chemical plant not just as some random collection of pipes, but as a carefully orchestrated ecosystem of interlocking systems. Every single piece of equipment relies on the one right before it and supports the one right after it, which brings up a massive question. How do we actually transform raw materials into precise, everyday products without causing a total catastrophe? We're talking about extreme temperatures, high pressures, and incredibly volatile substances. How on earth do we harness that kind of power safely?
Well, to answer that, we have to look at the very heart of the plant. The answer lies in our first stop, the reactor. You can basically think of a reactor as a giant, high-tech mixing bowl. It's specifically designed to safely contain and manipulate molecular transformations, forcing atoms to collide with enough energy to create something entirely new. In fact, the entire chemical plant essentially exists just to feed raw materials into this one piece of equipment and then clean up whatever comes out of it.
Moving right along to Phase 1, mixing and process reactors.
Now that we know what a reactor actually is, let's see how this translates into real-world production. Reactors come in lots of shapes and sizes, tailored to the specific chemical recipe they're cooking up. But operations are fundamentally divided into two types: batch processes and continuous processes. A batch reactor is kind of like baking a single cake in an oven. You load it up, the reaction happens, and then you empty and clean it. A continuous process, however, acts way more like an ongoing conveyor belt of chemical transformation. It literally never stops. Raw materials are pumped in one end at a constant rate, and finished products continuously flow right out the other.
Now here's a totally wild rule of thumb for chemical plants. Reaction rates generally double for every 10 degrees centigrade increase in temperature. This means heat is the ultimate driver of efficiency. See, atoms are always in motion, but they move much, much faster at higher temperatures. And those faster-moving atoms collide more often and with significantly more energy, which massively increases the chances that a new product will form.
But here's the catch. Because some reactions greedily absorb heat, while others violently give it off, reactors have to be equipped with special coils and jackets to prevent the whole system from either freezing solid or straight-up exploding. Endothermic reactions need external heat applied, like hot water or steam, just to keep the reaction alive. Exothermic reactions are the exact opposite. They generate their own intense heat, so they require a constant flow of cooling water to keep them from spiraling completely out of control.
What's really fascinating is seeing this in action inside a fluidized moving bed reactor, something like a cat cracker, which constantly cycles solid catalysts to break down heavy oils into valuable gasoline. Let's walk through how this works. First up, heavy gas oil is vaporized and mixed with a hot catalyst. Second, that intense mixture cracks the large, sluggish hydrocarbon molecules into smaller, highly useful ones. Third, a cyclone separator steps in to isolate the valuable hydrocarbon vapors from the catalyst, which by now is heavily coated in waste carbon. And fourth, that exhausted catalyst drops into a regeneration chamber, where blowing air literally burns the carbon right off it, leaving it hot and perfectly ready to be recycled back to step 1.
Which brings us to Phase 2, heating and cooling systems. Because our reactors generate such extreme conditions, our next stop has to be the climate control systems that keep these volatile chemical reactions perfectly stable. If you don't control the heat, you absolutely do not control the plant. Our thermal workhorses here are cooling towers, condensers, and reboilers. Think of them as the hidden HVAC system of the plant. A cooling tower drops hot water down through an air draft, using simple evaporation to cool the water so it can be reused. A condenser, usually a shell-and-tube heat exchanger, runs cooling water through tubes to turn hot product vapors on the outside of the tubes back into a liquid state. And finally, a reboiler does the exact opposite. It uses steam or hot oil to heat and vaporize liquid products, which usually drives the natural circulation at the base of a distillation tower.
And that perfectly sets up Phase 3, separation and refinement operations.
Once our raw materials have reacted and the temperature is under control, we enter the cleanup crew phase. The reality is, a reactor rarely produces a perfectly pure product on the first try. Usually, it produces a messy soup of mixed hydrocarbons. And here's the tricky part. They're all mixed together in a single liquid solution, looking totally identical to the naked eye. So how do we sort them out without manually filtering every single drop?
While here is the incredibly elegant solution: distillation. Distillation utilizes the unique vapor pressures of different chemicals to sort them by heat. It's almost like sorting physical objects by their weight. Because every single liquid has a totally distinct boiling point, we can slowly apply heat to a mixture. The lightest component, meaning the one with the lowest boiling point, will vaporize first. We capture that vapor, condense it back into a liquid, and boom, we've successfully separated it from the heavier liquid left behind.
Now, it's incredibly easy to separate liquids with a high relative volatility. Take pentane and heptane. Pentane boils at 96 degrees Fahrenheit, while heptane boils way up at 209 degrees. That's over 100 degrees apart, so separating them is a breeze. But what about low relative volatility? Butane boils at 31 degrees Fahrenheit, and isobutane boils at 11 degrees. That's just a 20-degree difference. To separate those, a single boil simply won't cut it. Operators have to rely on massive, multi-stage distillation fractionators that perform this vaporization and condensation process over and over again on dozens of different levels.
Let's actually look inside one of these distillation towers to see how this creates a continuous sorting machine. The feed liquid enters right into the middle of the tower. Because of a sudden drop in pressure, it immediately flashes into a mix of liquid and vapor. The lighter vapors naturally rise up into the cooler rectification section, while the heavier liquids drop down into the hotter stripping section. Along the way, they interact on specialized sieve trays, condensing and revaporizing until distinct, highly pure products can be drawn off at specific temperature levels from the top, middle, and bottom of the tower. Of course, distillation isn't the only tool in the shed. Operators also utilize things like multi-effect evaporators, paddle-type dryers, and resin-based ion exchangers to refine products down to their absolute atomic purity. If you need to concentrate a liquid, you use an evaporator to boil off the solvent. If you need to turn a wet cake into a dry powder, you bring in a drum or paddle dryer. And if you need absolute next-level purity, an ion exchanger uses special resins to literally attract and trap specific unwanted atoms, swapping them out for harmless ones.
All right, finally, we arrive at Phase 4, flaring and safety systems.
This is absolutely the most critical part of our tour. In a plant dealing with massive pressures and highly flammable materials, things are occasionally going to go wrong, and you need a foolproof way to safely release that pressure. When excess pressure builds up in a reactor or a distillation tower, those gases are routed to a flare system. But managing waste gas isn't just about venting it out into the open, it's about safely combusting it. Why? Because oxygen is the absolute worst enemy inside a relief system. The biggest danger imaginable is air creeping backward into the flare stack and mixing with those combustible gases. To prevent the deadly vacuum that could suck air back into the pipes, operators rely on a very precise sequence of safeguards at the flare stack. First, specialized molecular baffles and a physical pool of water act as one-way seals at the base. Next, a constant flow of purge gas sweeps the system, maintaining a positive outward pressure. Above that, pilot lights at the very top stay continually lit to ensure any escaping gas immediately catches fire. And to top it all off, infrared cameras constantly watch the flame. If they detect unburned carbon, which shows up as thick black smoke, they trigger steam injection directly into the flame. This creates turbulence that pulls in air for a clean, totally smokeless burn.
All of this incredible technology really highlights one crucial fact. Human operators are the true brains of the plant. You can have all the automated sensors in the world, but it still takes a skilled operator physically walking the plant to ensure safety and keep the ecosystem perfectly balanced. They're out there verifying the valves are lined up correctly. They're pulling product samples, checking pH levels, and looking for cloudiness. They're watching those infrared control screens. And they're literally using their ears and noses to detect a rattling pump or sniff out an overheating motor long before it ever becomes an actual emergency.
The incredible precision of these chemical plant systems creates the products we rely on every single day.
From massive distillation columns to high-pressure reactors, these plants are just awe-inspiring marvels of engineering, but they are completely reliant on human skill to tame them. So the next time you drink from a plastic bottle, put gas in your car, or rely on modern medicine, I want you to ask yourself, if a single closed valve can shut down an entire plant, are we underestimating the invisible operators who keep our modern world from going up in smoke?